Welcome to Spring LIB.
So in this question, we have two capacitors. One is 2.7 μF, and it was initially charged to 475 volts. And another one is 4 μF, and it is initially charged to 525 volts. So these capacitors are disconnected from the batteries, and the positive plates, let's assume this is positive, this is negative, this is positive, this is negative. The positive plates are now connected, and the negative plates are connected. So what will be the potential difference across each capacitor, and what will be the charge on each? So the total charge on the combination of capacitors is the sum of the charge on the two individual capacitors, because it's an isolated system. So there will be no neutralization of charge by combining positive and negative charges. So the voltage across each capacitor must be the same after they're connected, because each capacitor is connected to a corresponding plate on the other capacitor by a constant potential connecting wire. So we can use the total charge and the facts are equal potentials to find the charge on each capacitor and the common potential difference. So let's first find the total charge. Initially we have Q total equals Q1 plus Q2. Q is C times V, so this equals to C1 V1 plus C2 V2. But it also equals C1 V final plus C2 times V2 final. Okay, so this gives us V final, because when they stabilize, V1 and final and V2 final will be equal because they're connected, so I can also write this as C1 plus C2 V final. So V final equals C1 V1 initial plus C2 V2, that is the initial total charge, divided by C1 plus C2. So that is 2.7 times 10 to the negative 6 farad times 475 volts plus 4.00 times 10 to the negative 6 farad times 525 volts, divided by C1 plus C2, that is 6.7 times 10 to the negative 6 farad. This is 505 volts, and this equals to V1 final, and this equals to V2 final. And after we find that, let's try to So after we found that, we are able to find Q1 and Q2 afterwards, because Q1 final equals C1 final, C1 times V1 final, and Q2 final equals C2 times V2 final. And this equals 2.7 times 10 to the negative 6 farad times 505 volt. And this equals 4 times 10 to the negative 6 farad times 505 volts. So this is 1.36 times 10 to the negative 3 coulomb. This is 2 times negative 3 coulomb. So this is the charge on capacitor 1 and 2 after they're connected. So part B says what will be the voltage and charge for each capacitor if plates of opposite signs are connected. So what happens if we connect them this way? So the first thing we can see is that when you connect plates of opposite signs, what will happen is charge will flow and they might neutralize a little bit because the total charge will now be the difference of charge of the two plates. In other words, Q total becomes the difference of Q1 and Q2 initially. And it's whichever is larger, so it's the absolute value of Q1 minus Q2. And it is still equal to Q1 final plus Q2 final. So this is C1 V1 minus C2 V2 absolute value equals C1 plus C2 times V final. So this times we have V final equals C1 V1 minus C2 V2 divided by C1 plus C2. Again, we have the exact same equation as here, except that we change the plus sign to minus. And here we will actually end up getting an answer that is 120 volt. So you can see it's a lot smaller than the 100 volt. And we can find Q1F and Q2F in the same way. This is equal to C1 times Vf, which is the capacitors of capacitor 1 times 120 volt. This gives 3.3 times 10 to the negative 4 coulomb. This is C2Vf equals 4 times 10 to the negative 6 farad times 120 volt. This gives 4.9 times 10 to the negative 4 coulomb. 4.9. Okay, so that is the answer for part A and part B.